Welcome to Lecture 6. Last time we proved the negative binomial theorem, and there was a step in the calculation that was quite tricky. I'm returning to it here because the idea it contains will be very important going forward. To briefly remind you, we had defined the set M to be the set of all multisets on T types, and split that up into sets Mn. Each Mn is the set of multisets in M whose size is equal to n. All that's important here is that we have a big set M, and we split it up into sets Mn according to the value of some parameter, in this case size. The calculation went like this. We said that the sum over all n at least 0 of the size of Mn times x to the n is the same as the sum over all n at least 0 of a lot of copies of x to the n added together, where the number of copies is the size of Mn. And from there, we said that this is in fact the same as summing x to the size of m over all multisets M. You might find this last step to be the confusing one. To illustrate that what's going on here really has nothing to do with multisets and actually isn't so complicated, I'm going to turn to an example that's deliberately very down to earth. We're very lucky at Waterloo to have such strong undergraduate students, but that's not going to stop me talking about farm animals. Let F be the set of 8 farm animals as shown, and for each n, we'll let f sub n to be the set of all animals in F that have exactly n legs. You hopefully see the analogy with the multiset example. I have one big set and I'm dividing it up into small sets depending on the value of the parameter. I've written the number of legs above each animal, and from this we can see that f0 has size 1, f2 and f4 have size 3, and f8 has size 1. Now let's do a calculation that looks like the one for multisets. The sum over all n at least 0 of the size of fn times x to the n is 1x to the 0 plus 3x squared plus 3x to the 4 plus 1x to the 8. Now let's think about the sum on the right hand side. The sum over all animals in the set F of x to the power of the number of legs of that animal. If you think about expanding that sum, each animal will contribute one term, and the term it contributes will be x to the power of the number of legs. Because there are 3 animals that have 2 legs in the set, we will get 3 x squared terms. By similar arguments, we'll get 1 x to the 0 term, 3 x to the 4 terms, and 1 x to the 8 term. When we gather like terms together, we get exactly the sum in the middle. I hope these two examples shed some light on why this is the same principle being applied in both cases. Being mathematicians, we love giving the same name to different things, and that's what we're going to do here. We're going to define an object called the generating series for a set and a weight function that describes this power series you get by taking a big set and splitting it up according to the value of some parameter. We're then going to prove that no matter how you do this, you always get 2 different looking sums which are actually the same, just like you do in these examples. Here's the setup. We have an arbitrary set S, and we have a function w that assigns each element in S to a non-negative integer called the weight of that element. We call w a weight function. The set S could be finite or infinite, and it could contain multisets, farm animals, or binary strings or anything else. We now define a power series called the generating series for S with respect to the weight function w. This is defined to be phi sub S of x equals the sum of x to the power of the weight of sigma over all sigma in the set S. This is a generating series that contains exactly one term for each element of the set S. There is one extra condition we need for this definition. We don't allow the function w to be simply any function from S to the non-negative integers. We do require that for each non-negative integer n, the number of elements of weight n is finite. So for instance, if S is infinite, then w isn't allowed to assign 0 to everything in S. Usually this condition will be obviously satisfied for all the examples we're interested in. One final thing to note here is that even though we write phi s of x for this generating series, the generating series actually depends on w as well. You could argue that we really should have written phi subscript s and w of x. We leave w out simply for convenience, as usually the weight function is obvious from the context. We'll see a number of examples of this construction soon, but before that, I'll quickly prove the statement about generating series that makes them so useful. This is the exact same equality that we saw two examples of on the first slide. It says that the generating series for a set S with respect to a weight function W is the same as the sum over all n at least 0 of the number of elements of weight n in S times x to the n. In other words, the coefficients of this series count elements of each particular weight. To prove this, we first write down sets that describe how we split up the elements of S according to their weight. S sub n is going to be the set of all elements of S of weight n for each n at least 0. The definition of phi sub S of x is the sum of x to the weight of sigma over all sigma in S. Since S is the disjoint union of all the Sn's, this is the same as the sum over all n at least 0 of the sum over all sigma in S sub n of x to the power of n, because if sigma is in S sub n, then the weight of sigma is n. This summation on the inside is simply the sum of many copies of x to the n, where the number of copies is the size of the set S sub n. This gives us the next equality, which is what we wanted to prove. You can rewrite this statement in a useful form that emphasizes the value of each coefficient. For each k at least 0, the coefficient of x to the k in phi sub s of x is simply the number of elements in the set S whose weight is k. We'll be solving counting problems by reducing them to the problem of determining a coefficient in some generating series using this statement. At this point, we're overdue for some examples. I'll start with the one that we've already seen, although not expressed exactly in this language. Let S be the collection of all multisets on T types, and for each of those multisets, let the weight of that multiset be its number of elements. By the definition, the generating series for S and this weight function is the same as the sum over all multisets of x to the power of the size of that multiset. By the theorem we just proved, that's the same as the sum over all n at least 0 of the number of n element multisets on T types times x to the n. We know from last week that this is the sum of n plus t minus 1 choose t minus 1 times x to the n over all n at least 0, and we know from this week, the negative binomial theorem, that that's the same as 1 minus x to the power of minus t. This is pretty cool. The generating series construction gives us a way to go from a combinatorial setup to an algebraic object. Here, the combinatorial setup was multisets where the weight is the size, and the algebraic object that we got out of it was 1 minus x to the power of minus t, which is a nice function. Here's another combinatorial setup. Let S be the set of all binary strings, and let the weight of each string in S just be the length of that string. I haven't formally defined binary strings yet, but here's what the few shortest ones look like. We start with the empty string, which is traditionally written epsilon. This has length 0. Then there's two strings of length 1, 0 and 1. There's four strings of length 2, 0, 0, 1, 0, 0, 1, 1, 1, and so on. The generating series for this set is the sum over all binary strings of x to the power of the length of that string. By our theorem, that's the same as the sum over all n at least 0 of the number of binary strings of length n times x to the n. The number of binary strings of length n is not too hard to compute directly. To construct a binary string of length n, I have two choices for the first entry, two choices for the second entry, and so on. This gives me 2 to the n choices in total. Therefore, the sum is the same as the sum of 2 to the n x to the n over all n at least 0. This is a geometric series, so its sum is 1 over 1 minus 2x. So the generating series construction takes the nice combinatorial setup of binary strings and their lengths to an equally nice rational function, 1 over 1 minus 2x. Here's another nice example. Let S be the set of all subsets of 1 up to t, where t is some non-negative integer, and let the weight of each set in S be equal to the size of that set. You'll see a pattern in the kind of setup we're looking at here. Usually the set S will be a set of combinatorial objects of some type, whether they be sets, multisets, strings, or something else. Usually the weight function will be some notion of how big the objects in S are. This will be the length for strings, the size for sets, and so on. In this example, the generating series is by definition the sum over all subsets of 1 up to t of x to the power of the size of that subset. Note that there are only finitely many subsets of 1 up to t, so in fact this is a finite sum, unlike the previous two examples. By our theorem, this sum is equal to the sum over all n at least 0 of the number of n element subsets of 1 up to t times x to the n. In other words, it's the sum of t choose n times x to the n over all n at least 0. By the binomial theorem, this is 1 plus x to the power of t, another nice rational function. This last example is intended to show that this construction can do some very interesting things. Let S be the collection of all multisets where every part is odd. Unlike the last example with multisets, I'm not restricting the number of parts. It can be anything. It's hard to even write out all the elements of S in a sensible order, but some of them are here. Like our last multiset example, the weight of a multiset will simply be its size. Here, we'll make sure that this is actually a weight function. In other words, we need to know that for each n, the number of multisets in S on n elements is finite. This is true because the multisets in S all have odd parts. If I have a multiset in S of size n, then each part is at least 1, and each part is at most n, so there are at most n parts, each of which is at most n. This gives only finitely many possibilities. We don't have the tools yet to actually compute the generating series, but I'll tell you what it is. It's the series with a constant term of 1, where the rest of the coefficients form the Fibonacci sequence. That is, each coefficient starting with x cubed is the sum of the previous two coefficients. This sequence popping up out of nowhere might seem surprising. We also get a nice rational function for this generating series. It's equal to 1 minus x squared over 1 minus x squared. We'll see why this is true next week, but if you're interested, it's probably something you could prove now by induction on the sequence of coefficients. In all those examples except for this very last one, we computed the generating series using theorems we'd already proved from elsewhere. This was nice to be able to see some examples, but it's not really the point of generating series. The point is to use them to solve new problems. Next week, we'll see the tools that you can use to do that. Thank you for watching.